45 minutes. Jeez. Okay, so. Say it again.
Homework is not open on campus.
It's probably going to open at 5:30 would be my guess, but just, you can go ahead and email it to me just in case, okay? So I don't know why it's not already open, but if it doesn't open at 5:30, just email your response to me. Okay, all right, so I got to get going because I have a lot to get through today so that we can get to the story next Tuesday, which is general relativity. Okay? So next Tuesday is when we're actually going to crank out what is general relativity. But let me get through what we're going to do today. So what we're going to talk about today is the notion, oh boy, that marker's dead. We can start the fun little marker game of conserved quantities and space-time symmetries. Now, the notion of conserved quantities is something which you've hopefully seen and hopefully used before. And so what we're going to do today is we're just going to look at how this story plays out in general relativity. It's a little bit different than what you're used to. So just to remind you, from the Euler-Lagrange equations, in a non-relativistic system of point particles, we tend to have something like this. Okay, everybody's familiar with the Euler-Lagrange equation? Yes, no, maybe, perhaps? Good, all right, that's awesome. I'm going to try another marker. Hopefully this is gooder. Okay, well, we can immediately see that if, and by the way, this is how we define, ooh, look at that, that's working. That's how we define the momentum conjugate to the coordinate xi. But what we find is that the derivative of the momentum with respect to time equals, of course, the partial derivative of the Lagrangian with respect to the coordinate xi. And this, of course, tells us that if the Lagrangian does not explicitly depend on the coordinate xi, then the derivative of the momentum in that direction is 0. Okay? Which means the momentum is conserved. All right? So this is this standard observation that should have been given across to you in Physics 350, where if you're writing down a Lagrangian and it doesn't depend on a particular coordinate, then the momentum along that coordinate is conserved. Okay? If it does explicitly depend on a coordinate, then clearly the momentum is not conserved. Okay? Now, this is the simplest possible argument you can make for a conserved quantity. The more general argument is due to Emmy Nether, and this also applies to field theory calculations. But generically, what Emmy Nether proved is that if you have a continuous symmetry of an action, then that continuous symmetry will always give rise to a conserved current. Okay? So, conserved quantities, hopefully, you've used them before to solve problems. They're very simple for the purposes of applying to solve problems. The work energy theorem, the impulse momentum theorem, those were conserved quantities that you learned and dealt with and worked with in Physics 100 at least. Now, in this class, we are not ever going to write down a Lagrangian formulation of general relativity. We could, but we're just not going to go there. Okay, we're just going to work straight with the equations, so we're not going to try and derive them from a Lagrangian. So you might wonder, how are we going to get conserved quantities in general relativity if we don't have a Lagrangian? We could get them from the Lagrangian, but we're not going to go there. And so I'm going to develop a slightly different approach to figure out how to get conserved quantities in general relativity. And the result is going to be a little bit different than what you've seen in this standard Lagrangian example. Okay. So I feel like I'm like super rushed and feels weird. Anyway, okay. So first of all, if we want to argue that the momentum along some direction, I'll just call it the star direction, is conserved, this is a highly coordinate dependent statement, okay? And what we're going to do is we're first of all going to go ahead and derive how this condition happens in general relativity in this highly coordinate dependent form. We'll get a result. It'll be like, oh, that totally makes sense. And then we'll take a step to a coordinate independent version of the same story. And this is going to involve something whose name is awesome. So just hang on, okay? So let me start with the coordinate dependent version of this story. And in order to do this, let's start out with the geodesic equation, which can be written in a couple of different forms, but I'm going to use this form for today. Okay, the version of this that you probably used in doing your homework is a slightly different one, where you actually put in what the covariant derivative looks like, and then you collect terms. It's got the explicit Christoffel connection. But this is going to be enough for us. So the path x nu or x mu is geodesic if this satisfies that this is 0. And of course, one thing that we can do with this expression to make it in terms of other nicer quantities is to say, oh, well, first of all, this is the length of the space-time interval, so this is tau. You could parameterize the path with anything, but I'm actually using what we call the proper time or the length of the path, because if I multiply this by the mass squared, it's still equal to 0. But if I put one of the mass terms here and one of the mass terms here, what do these become? Sophia!
Yes.
What do I get if I do m times dx nu d tau?
Is it going to be 0?
No?
No.
No?
Sorry, that was my first thought.
That's fine. This is our definition of 4 velocity. So if I multiply,
man.
say it again?
I said, oh man, is it going to be a little bit long?
No, it's 4 velocity times mass. What do you think that defines? You've got some help in the class.
What?
Say it.
So,
Oh, come on.
it's hard to read, I can't tell.
It's okay.
Okay. What did I just write, Sophia? Yeah, the 4 momentum. Thank you. Okay.
That's what I was going to say, but I didn't know if you're pointing at me or not.
Okay, that's fine. That's fine. That's fine. Let me continue. Okay, so now I'm just going to massage this a little bit. Okay, so bear with me. This is just index massaging. There's nothing deep. There's no manifolds, no maps, anything. I'm just doing some index massaging. So hopefully after that homework, this is something that will be easy for you. So the first thing I'm going to do is I'm going to hit this. I'm going to hit both sides of this with a factor of g alpha mu. And then I'm going to use a very important property of the metric with respect to the derivative, and this is called the metric compatibility property, which was part of our derivation of the covariant derivative. That is, the metric, even though it's a function of where you are, the metric can always move past the covariant derivative. That this is possible was part of our definition of the covariant derivative. It is not obvious, because this is a function of where you are in general. So the fact that you can arbitrarily move it past the covariant derivative is not obvious, but it is a condition. And so you can go back to where we define the covariant derivative to understand that. But what we can do is we can use this to lower this, and likewise to lower this. And so that's going to create this following version of the statement that we've basically lowered, and I should actually act with the metric over here instead of over there, because it kind of looks like I'm cheating anyway. But anyway, all right, so this is just lowering the index on the second momentum factor, but here we go. Let's write down what the covariant derivative looks like. This is something with which you should all be relatively familiar now. Okay? Just expanding the covariant derivative. And now what we can do is we can say, okay, I'll collect these terms, P nu, D nu, P alpha, minus P nu, gamma, lambda, mu, alpha, P lambda. Okay? And now we can do some massaging. So this I can write as m dx nu d tau partial nu P alpha. And this I can write as P nu, and then I'm just going to put in our final expression for the Christoffel coefficient, okay? So remember, the Christoffel coefficient is given by G lambda beta times a bunch of derivatives of the metric. Times that guy, okay? And so we can now simplify this a bit. This is simply m times the derivative of the form momentum along the path parameterized by tau, okay? So this is just a line, this is just a path integral, or sorry, a directional derivative, okay, expressed in terms of the coordinates here. So we're just collapsing it back to the directional derivative. All right? Now this guy, I can take, okay, so this is what I'm going to do. I'm going to take all the terms in parentheses, and I'm going to swap the order of these because the metric is symmetric. You'll understand why I did that in just a second. D alpha G beta nu minus D sigma, sorry, no, not D sigma, D beta G nu alpha. Okay, and then I'm going to use this metric to raise that lambda into a beta, and so this is now going to have P nu P beta. Okay? We good? Now there was a trick that I taught you a couple of lectures ago, and we're about to use it. You ready? What happens to the term in parentheses if I swap nu and beta? Anyone? Do I need to take a part? I'll take a part. Yeah, it's the negative of it. Okay, because this term becomes this term, and this term becomes this term, which is the same thing except with the minus sign. So this guy is anti-symmetric in nu and beta. What about that guy?
Do those commute?
Yeah, they're just form momentum.
Then it's going to be the same, right?
It's not the same. These are symmetric under the exchange of nu and beta. If I swap nu and beta, this is the same expression, okay? Now who remembers the tool? Go for it.
An anti-symmetric tensor times a symmetric tensor is just going to be 0, right?
Yes, if you're summing the anti-symmetric indices with the symmetric indices, you get 0, okay? So this whole term is 0, and then the only piece we have left is minus 1/2 d alpha g beta nu p nu p beta, okay? Which of course tells us that this guy is 0 if this guy is 0. All right? Well, look at that. dp alpha d tau equals 0 if d alpha g beta nu equals 0. This is saying, in analogy with this story, remember in this story, if the Lagrangian doesn't depend on the coordinate, then the momentum along that direction is constant. Okay, this is actually a conservation because these are 4 vectors. Okay? I'll interchange the words constant and conserved, but I really mean conserved in all cases. Okay? Well, it's constant in this context. In this context, it's conserved. Okay? But nonetheless, the momentum along the alpha coordinate is conserved if the metric does not depend explicitly on that coordinate. Okay? Does this make sense? All right, good. So, there you have the general relativistic version of this story, where this is really focused on the geometry. Okay? But once again, this is very coordinate dependent. I mean, after all, if I'm working in R3 with x, y, and z, well, then the metric is just 1, 1, 1. Then the metric doesn't depend on any of the coordinates. So this means that px, py, pz are all constant. Okay? However, in the same space, in spherical polar coordinates, the metric takes the form so naively, the only thing we would argue is constant is the phi momentum. Because the metric in this case depends on both the radius and the angle theta. So these coordinate dependent versions of this story are not that useful. Okay? Remember, we can take the metric and we can transform it with a different choice of coordinates into any crazy form we want, almost every crazy form we want. So this coordinate dependent version is not going to be very good for finding conserved quantities. So let's uncover a better method with a really cool name. So here we go. So suppose that we had a component of the momentum which was conserved. Okay? Now, I want to point out, this is not the same as dp mu d tau, where this has got all 4 of the components of the momentum. This is just a particular component. That's the star. It's saying it's just this component. Okay? So, let's just suppose that we had a conserved momentum component. Now, what we're going to do is we're going to introduce a vector k mu such that k mu combined with a dual momentum vector gives us the component p sigma star. Okay? So just as an example, imagine that the x component of the momentum was conserved. Then the vector, and I'm talking about in a R3. Then the k vector, we might write it like this, would just be 1, 0, 0. Okay? Because if I take the k vector with an arbitrary momentum vector, it's going to be 1, 0, 0, px, py, pz. Sorry, I'm going back to R3, so I don't have to really worry about upper and lower. But nonetheless, if I now take this k vector and I do an inner product with the p vector, then this is just going to return the conserved component. So that's all this is doing. Okay? Are we on board? Okay, that's good. Now, on the other hand, I know the k vector, I can figure out the p. Because this is an arbitrary momentum. So if I somehow can find out what the k vector is, then that will tell me the conserved quantities. So let's get an equation for the k vector, and then we'll name it. So here we go. We want the condition that dp star d tau equals 0, but of course p star is k mu p mu. Okay? And we can write this. Okay, so this is the directional derivative, but we can give it a coordinate dependence by saying, okay, well then what I do this is dx nu d tau d nu k mu p mu. Oh, I'm actually doing it this way. I don't know why I'm doing it this way, but I'm doing it this way. It doesn't matter which way you do it. Okay. This is the same as k mu p mu. It doesn't matter which one's up and which one's down. Okay? So now I'm writing a normal derivative because this is what kind of quantity? Hold on, I'm going to draw a card. N. Aaron. Joel. It's a scalar. Okay? This is a scalar. That's the reason I'm hitting it with an ordinary partial derivative. Okay? But if I would like to use the product rule with the derivative, I can't leave it as this. I have to promote it to a covariant derivative. Okay? So we can also write this as dx nu d tau del nu of k mu p mu. Okay? And now I can use the product rule. And this is going to give me, and I'm also going to multiply this expression because it's equal to 0 by another factor of m to make this a momentum. So times m, 0 is equal to p nu times, okay, so I can do p mu del nu k mu plus, this is just letting the derivative act on the k mu, pulling this p mu out, and it's just p nu times p mu. Again, the mass factor is combining with this to give me a p nu. Okay, and then we have the other term from the rule, k mu p nu del nu p mu. Okay? Does anybody see simplification? What? What do you see? Nope. I'll point it out to you. What is this? Look on the rest of the board. It's 0. Okay? So what we can argue is that p nu p mu del times the symmetric combination of these indices, and hold on, I'm going to, oh sorry, hold on. Oh sorry, this should be lower. There we go. Yeah, my bad. Okay, so times the symmetric plus this times the anti-symmetric. Okay, and there's a factor of a half that's missing, but remember, anytime we have a second-rank tensor, we can always split it up into a component which is symmetric under the exchange of the indices, and then a part which is anti-symmetric under the exchange of indices. Is everybody familiar with that rule? Do I need to show you with a simple matrix? Who needs to see it? Raise your hand. Okay, that's fine. So Yeah, so if I give you a matrix M, then you can always write this as 1/2 Mij. You can always write this in the following form. Okay? Where this thing, and I'm just, take it as a, yeah, we'll do this. So we'll say that Mij, and my factors of 1/2 might be out, but Mij is basically taking the matrix and adding it to its adjoint, because this thing is intrinsically symmetric under the exchange of I and j. Even though the matrix itself might change if you interchange I and j, this combination obviously doesn't change, because I goes to j, changes this into this, and this into this, and it's the same. This guy is Mij minus Mji. Okay? Because this guy's the anti-symmetric combination. So if I take this and I swap ij, this becomes this becomes this with an overall minus sign. Are we on board? Now take this and add it to that. That goes away. We get a factor of 2 times 1/2. Does this make sense? So an arbitrary matrix can be decomposed into the symmetric and anti-symmetric combinations. That's all I'm doing here. I'm saying this is a 2-index object, so I can decompose it into a symmetric and an anti-symmetric combination. Are you ready? What's this term? Thank you. This is the second time I've made this argument today. This is symmetric, this is anti-symmetric, and those indices are being summed over. So this is 0. Okay? Does anybody want me to repeat why that happens? Okay. All right. So in the end, what we have is that if del, and maybe I'll write it down here. If del nu k mu equals 0, because these 4 vectors, these 4 momenta are definitely not 0. Okay? So if the covariant derivative of the k mu vector symmetrized over the indices equals 0, then k mu is a symmetry of the geometry. Okay? And k mu, p mu is conserved. Now, why is this way more powerful than this story? Louis.
Hello.
Hi. Why is this expression more powerful than this story that I gave you here?
Is it because it's more applicable?
It's more applicable, why? What's it written in terms of? Anyone? Say it again? All right, I can't hear you. Sorry, say it one more time. Exactly. This is written in terms of tensors. This is a tensor equation. This equation is true in any coordinate system, because this transforms like a tensor. So if you change coordinates, this is just going to get those 2 factors. This is just going to get those 2 factors, so it's going to remain 0. Okay? This was highly coordinate dependent. Remember the example I gave you with R3 with XYZ versus R theta phi? That's a very coordinate dependent thing. This is coordinate independent. This is the equation you can solve and however many k vectors you have, that corresponds to the number of conserved quantities. K vectors are awesome. Let's call them killing vectors. Yes. Okay, so this is Killing's equation, and the k's that are solutions to it are called the killing vectors. Okay? Now what's astonishing about killing vectors is if I took R3 with R theta phi, okay, I would find 3 killing vectors. Because there are 3 obvious symmetries. Even though the metric depends on R and theta. So if you just look at the metric, you might be like, oh, it depends on R theta, therefore this. No, there's 3 killing vectors. Okay? And if we solve Killing's equation, we'll find those 3 vectors. And I'm going to do that as an example if I have time. I don't know if I'll have time. Okay? But, at any rate, so, now we'll ask, how many killing vectors should we expect? And the answer to that is, well, depends on the space. Some spaces have 0 symmetry. In fact, real space has 0 symmetry. There's no translational invariance, there's no rotational invariance, there's no time translational invariance. It's just that the universe is just a confused thing. But anyway, we'll deal with lots of solutions that are symmetric. Okay, so what we'd like to know is, how many killing vectors can you have? Okay, and remember, these are space-time symmetries. These aren't the abstract symmetries of some abstract vector space. This is space-time. And it turns out that there's a maximal number. And this corresponds to the symmetries of what is called a maximally symmetric space. Says. Okay? So first and foremost, recall that because we're working with manifolds only, locally, you can zoom into a point and write the coordinates such that the space looks like what?
Flat space.
Flat space. Okay? So if you're in a Euclidean signature space, you can make it look like Rn, or if you're in a Lorentzian signature space, you can make it look like Minkowski space. Okay? Euclidean signature just doesn't have a time. Minkowski has the time. Okay? However, we can figure out how many symmetries are associated with Rn and Mn simultaneously. Turns out there are n translations and 1/2 n times n minus 1 rotations in Rn, or Lorentz in Mn. Okay? The counting is the same. So you can obviously translate along each coordinate in flat space. That's the n translations, where n is just the dimension of the space. And then you can do 1/2 n times n minus 1 rotations if you're in Rn, or Lorentz transformations. And remember, in Minkowski space, Lorentz transformations include the rotations. Okay, so in Euclidean space, you only have rotations. In Minkowski space, you have the full Lorentz group, which includes the boosts and the rotations. We remember that? Okay, that's why there's an or here. Okay. Together, these form the Euclidean or the Poincare group. Those are some names that I gave you before, but I just want to shout out, in total, we have n plus 1/2 n squared minus 1/2 n, which gives me 1/2 n times n plus 1. Okay? I'm just adding these two numbers together. So here we go. Let me pick a sufferer. Danny, in 4 dimensions, How many do I have?
10?
10. Okay? Now here we go. These are the symmetries of the zoomed in tiny patch, which we've written our coordinates so that it either looks like Rn or Mn. Okay? In that little tiny patch, we'll have these 10 symmetries. But now we can step back and say, suppose the entire space has that many symmetries. Okay? Then the entire space is what's called a maximally symmetric space. Now you might be sitting there going, duh. If you step back and demand these symmetries, then you're just making the whole space Rn. Or you're making the whole space Mn. Duh. No. It's not true. Okay? Let me give you an example. Consider the surface of the sphere. How many dimensions does this space have? This is a two-dimensional space. What's the maximum number of symmetries that you can have in this space? 3. Okay? Well, let's just go to the North Pole and ask ourselves, well, actually, let's just pause. Is it obvious that you have 3 symmetries of this object? 3 independent symmetries. You can imagine those as rotations around the x-axis, rotations around the y-axis, and rotations around the z-axis. So there's the immediate argument, hey, there are 3 symmetries. But remember, the symmetries should be related to 2 translations and 1 rotation. Well, here we go. If we go to the North Pole, then around the North Pole, a rotation around the y-axis or the x-axis is actually a translation, whereas a rotation around the z-axis is a true rotation. Okay? So the local picture of this still gives you 2 translations and 1 rotation. Even though in general, looking at the entirety of the space, you would just call the symmetries 3 rotational symmetries. But here's the important point I'm making. This space is maximally symmetric, but it is not Rn or Mn. This is a curved space. It's not flat. So you can obviously have curved spaces which are maximally symmetric. Okay? Now, maximally symmetric spaces do not have to be flat, but if you know that a space is maximally symmetric, its curvature has to take a simple form. Okay, the curvature can't be that complicated. All right? And in fact, what we can say is the following. And I'll probably regret erasing this in just a moment, but we'll see. Actually, let me just hang on to this because that's what I'm going to need. Okay? First of all, the curvature tensor is R nu rho mu. That's lambda. I don't know why I have. Oh, no, sorry. I just want to get my indices right, so what I write down later is correct. Okay? So this is the best measure of curvature of a space. That's the Riemann curvature tensor. Okay? In general, this can depend on where you are in the space. The curvature tensor can be a function of where you are, unless your space is maximally Translational.
Translational symmetry won't allow.
Yeah, maximally symmetric spaces have translational invariance. That means if you know the Riemann curvature tensor at this point, the Riemann curvature at this point better have the same value. So in a maximally symmetric space, it's just a constant. Okay? Still has 256 components, but it's a constant. It doesn't change as you move from point to point. Okay? However, it gets better than that because it turns out that if we know the Ricci scalar and the metric, remember the Ricci scalar is the full contraction of all of the indices. If all we know is the Ricci scalar and the metric, we can construct this using the following expression. R lambda rho mu nu, this is just dropping the first index using a factor of the metric, is equal to the Ricci scalar over n times n minus 1, where n is the dimension of the space, or space-time, times g lambda mu, g rho mu, minus g lambda nu, g rho mu. This is a hell of a lot easier to figure out than what we had for our definition of the Riemann curvature tensor from a couple of lectures ago. Actually, maybe last lecture. All right? So if I gave you the Ricci scalar for the space and the metric, you can bang this out super easy. Now remember, this tensor had some symmetries. If you exchanged lambda and rho, you had to get back minus what you started with. If I exchange lambda and rho, oops. Oh yeah. So if I exchange lambda and rho, then this becomes rho mu g lambda nu minus g rho nu g lambda mu. Okay? But then I can just reverse the order of these, in which case this becomes this becomes this, and it makes up in a rho minus sign. Okay? If I exchange mu and nu, the same thing happens. If I take these two and I swap them, I get back the same thing. So you'll notice this shares all the wonderful symmetries of the Riemann curvature tensor. All right? Okay? Now, here is a catalog of maximally symmetric spaces. You might wonder, well, what are there? And it turns out it's only a handful. And they are categorized by what the Ricci scalar is. If the Ricci scalar is 0, then under Euclidean signature, that is, this is just a space, it's not a space-time. So we have Euclidean and we have Lorentzian. The Euclidean signature spaces with r equals 0 include Euclidean space and tori. Where tori, of course, are just the topologically non-trivial deformations of Euclidean space. So if Euclidean space is this infinite plane, I can just take a finite piece of it, wrap this around, and form a cylinder. That's a torus. It's still flat. I know it looks curved, but trust me, this is flat. Okay? And it turns out that you can take a donut, which is the way you might think of a torus, and you can actually, in the right number of dimensions, show that this is flat. Even though in 3 dimensions, it turns out this is curved. In 4 dimensions, this is flat. You curious about that? You're going to prove it on your homework. Okay, but at any rate, if r equals 0, and you have a Euclidean signature, that means you're only spatial. You're either Euclidean space itself, Rn, or you're a torus. If it's a Lorentzian signature, then you're in Minkowski space, or you're in Minkowski space tensored with tori. Okay? just need Minkowski space somewhere in there because that's got your time ingredient. Now, if R is greater than 0, what kind of Euclidean spaces are going to have a curvature scalar, R, which is positive? Any guesses? They have to be maximally symmetric. I'll give you a hint. I just drew one on the board.
S2.
Yeah, Sn in general. Okay, the nth dimensional sphere is a maximally symmetric space with positive curvature. Okay? What if R is less than 0? Any takers?
Is that a hyperbolic?
Exactly, that's a hyperbolic space. Okay? And now for the big one. What is a Lorentzian version of a maximally symmetric space with positive constant curvature? Anyone know?
Is it Minkowski space tensor product with the Sn?
Ooh, that's actually cheating. It is, but there's a general name for this kind of space. That's interesting. This space is called de Sitter space. Okay, and then I'm going to give you one guess for what the negative curvature is. Exactly, it's anti-de Sitter space. Okay, that's it. I mean, if you think about it, I just categorized all of the possible values of R. There's positive, negative, and 0. Okay, so that's it. These spaces play a very important role. Because in truth, we don't live in flat space. We live in a space which at first glance is mildly curved. If you remove all the garbage in the universe and you just smooth it all out, it's either de Sitter or anti-de Sitter. Anti-de Sitter actually plays a huge role in string theory calculations, which we're not going to get into in this course. Boo. Okay? But de Sitter actually ends up being the form of a background space-time which is relevant for our universe. Okay, so I'm going to, since you guys took a little longer on the quiz, I'm going to take an extra 5 minutes and work through an example, because I think this is important. If you need to go, get up and go, but please stick around if you can. I'm just going to get to an example. But what I'm going to do is I'm going to solve this equation for a space. And just show you that the solutions to this do in fact give us conserved quantities. Okay? And I'll just go through it quickly, making a few important comments along the way. So here we go. First of all, let's do S2. Okay? So with the angles theta and phi as the coordinates for the S2, we know that ds squared is d theta squared plus sine squared theta d phi squared. So this is a two-dimensional sphere with radius of 1. So there's a r squared here, those are just 1. This, of course, immediately tells me that the metric on the space is 1, 0, 0 sine squared theta. And this, of course, tells me that the inverse metric is 1, 0, 0, 1 over sine squared theta. Okay? After your homework, this should be relatively familiar to you. Moreover, the non-zero Christoffel symbols you should now appreciate to be gamma phi theta phi equals gamma phi phi theta, which is cotangent of theta. Gamma theta phi phi is minus sine theta cosine theta. And all the others equal 0. Okay? So these are the only 3 non-zero Christoffel symbols in this coordinate system of this space. Now, what we want, well, first of all, what do we expect? How many solutions do we expect? 3. Remember, this is a maximally symmetric space. It's two-dimensional, therefore 3. Okay? So we expect 3 solutions to this expression. So let's do it. First of all, let's expand it out. D mu k nu minus gamma lambda mu nu k lambda plus d nu k mu minus gamma lambda nu mu k lambda. Okay. All I'm doing is I'm putting in the covariant derivative and then I'm doing the symmetrization between mu and nu. So this is this with mu and nu interchanged. Okay? Now I can simplify this to d mu k nu plus d nu k mu minus 2 gamma lambda mu nu k lambda, because remember the Christoffel symbols are symmetric under the exchange of these lower indices. So these two things are actually the same. So we'll just combine them. Okay? Now, how many distinct equations do I expect this to give me? Not scalar equations, but component equations. This is a 2 by 2 matrix, right? However, it is a symmetric matrix. So how many independent components does a symmetric 2 by 2 matrix have? 3. The diagonals and then one of the off diagonals, because the other off diagonal has to be the same. So there are 3 independent equations, and I get them just by picking the coordinate values for mu and nu. So here we go. Let's do mu equals nu equals theta, in which case I get 2 d theta k theta minus 2 gamma lambda theta theta k lambda. I can choose mu equals nu equals phi, in which case I get 0 is 2 d phi k phi minus 2 gamma lambda phi phi k lambda. And then I can do mu equals theta, nu equals phi, and this will give me the same equation if I give this phi and this theta, so I'm just going to do it once. And this is going to give me 0 is d theta k phi plus d phi k theta minus 2 gamma lambda theta phi k lambda. Okay? All I'm doing is I'm giving assignments to mu and nu. There's 3 independent possible assignments. I could have done these reversed and then get the same equation. Now all I do is I take these and I dump them in. Okay? And so we end up with d theta k theta, because this guy is 0, and the number 2 doesn't really play a role in a story of something being equal to 0. This is going to give me d phi k phi plus sine theta cosine theta k theta, because the factor of 2 is not going to play a role in the story because this is equal to 0. And I do have a non-zero gamma lambda phi phi. It's right there. And then last but not least, we have d theta k phi plus d phi k theta minus 2 cotangent of theta k phi. Okay, got to keep 2 around this time. It's not an overall factor. Okay? Now, I am going to give you the 3 solutions to this. The 3 vectors k nu, or k nu, or whatever you want to call it, k nu. These 3 solutions must satisfy all 3 of these equations simultaneously. I'm not going to solve them, I'm just going to give you the solutions. But they have to satisfy, each solution has to satisfy all 3 of these equations simultaneously. That's important. Because this is the single equation of which they are a solution, and this is just breaking it down into its components. So if you satisfy this equation, you satisfy all 3 of these in this particular coordinate system. So here we go. Here are our solutions. K1 mu is 0 sine squared theta. K2 mu is sine phi 1/2 cosine phi times sine of 2 theta. I'm giving you the theta phi parts of each of these vectors, or dual vectors actually. And maybe I should have called them nu, it's fine. And K3 nu is, whoops, cosine phi minus 1/2 sine phi sine 2 theta. Okay? So these are just the solutions to Killing's equation. As we expected, because this is a maximally symmetric two-dimensional space, it has three spatial symmetries, each of them represented by the independent solutions to this equation, and there are 3 of them. Okay? I don't want you to match this number with this number. That's not necessarily true. Okay? If this were a non-maximally symmetric space and it only had 2 conserved quantities, you would get 2 solutions to these 3 equations. Okay, so don't take 3 to mean 3. I mean, you can't have more than 3, obviously. Okay? Now, just to finish the story, remember that once you've found the Killing vectors, this tells you that the momenta, which are conserved by each of them, I get, and I don't know why I'm using u's, I'll use news. But to figure out what component of momentum is conserved associated with each of these symmetries, I just take the dual Killing vectors and I contract it with an arbitrary 4 momentum. Okay? And then in this case, this first one gives me sine squared theta p phi. The second one gives me sine phi p theta plus 1/2 cosine phi sine 2 theta p phi. And I'll let you figure out what the last one is. It's pretty simple. Okay? All of these enjoy that the derivative with respect to tau of each of these is 0. Okay? Well, again, this is a 2-sphere. And the 3 symmetries that these are describing are globally the 3 rotations you can do. But to put this in a more familiar language, we'll do what we did before. That is, we'll zone in on the North Pole, and we'll say, okay, near the North Pole, a rotation around the x-axis and y-axis are translational, and then the rotation is around z. So it turns out that the momentum components described by those 3 Killing solutions are nothing but the angular momentum around the z-axis, the x component of the linear momentum, and the y component of the linear momentum, which is what we would expect. Whew. Okay? Any questions? Okay, sorry for keeping you a bit long. Next Tuesday, so you will have a homework due next Thursday. Next Tuesday, though, is where we're going to get to the meat of general relativity. We're going to look at Einstein's equation finally. And we will even extract the Newtonian limit from it. I'll see you then.